Let's start the actual contents of the course by starting to talk about the continuum hypothesis. As I mentioned earlier, the reason this is because the conservation laws that we're generally familiar with, conservation of say momentum or conservation of energy, when we learn classical mechanics, we normally apply these laws to point objects. Extended objects, all right, but extended objects are merely a collection of point objects, and they're associated. Most of the time you idealize for instance the trajectory of a stone to the trajectory of the center of mass of the stone. Yeah, so this is what we are generally used to. However, here in this course we are not talking about point objects. We are talking about a continuum. Say consider the flow of air or water. So this is an aggregate. This is an aggregate of many molecules. Yeah. So this is what I mean by saying that this is essentially a sub branch of continuum mechanics, as opposed to the mechanics of point bodies. And in particular, we do not concern ourselves with microscopics like collisions between atoms and molecules. Yeah, this is what one does in the kinetic theory of gases when one wants to understand concept like pressure of a gas. For instance, you have a gas in a container. So what causes the gas to exert pressure on the walls of a container? That's because the gas has a finite temperature, and therefore the molecules are constantly buzzing about, and they're constantly striking the walls of the container and then bouncing back, and so the impulse manifests itself as pressure on the walls of the container. However, we will not be concerning ourselves with those microscopics. We will instead be concerning ourselves with the macroscopic effect of these microscopic collisions, aka pressure, for instance. So pressure will be one quantity we'll be invoking quite frequently. So everything, of course, derives from collisions, but we will not bother so much about the we will have a sandpaper to smooth over. We will be resorting to what's called coarse grained description of these things. We will be looking at a fuzzier description, and we will be concerning ourselves mostly about the macroscopics, so macroscopic quantities such as pressure, density, velocity, and so on and so forth. Pressure, density, velocity of the continuum, not of the constituents of the continuum per se. Yeah. Materials also are characterized only by the bulk properties such as conductivity, elasticity for solids, elasticity and viscosity applied to fluids, and elasticity applied to solids. Of course, there are complex fluids which are viscoelastic. We won't go into those complexities, but roughly speaking, we will be concerning ourselves only with these bulk properties, which some people like to characterize, like to describe as emergent properties, properties that emerge from microscopics such as collisions. These bulk properties, of course, for instance conductivity or viscosity, they are characterized by the relevant transport coefficients. You can think of the coefficient of conductivity. Yeah, conductivity of what? Say heat. So the heat conductivity of copper is more than that of aluminum, for instance, which is why we think of copper as a better conductor of heat than aluminum. Well, where did this come from? Concept of conductivity, which is one transport coefficient. Examples of other transport coefficients are a viscosity coefficient and elasticity modulus, so on and so forth. So this transport coefficients came from microscopic properties, which we will not bother about. But it's important to keep in mind that they come from microscopic properties. Yeah, instead of bothering about the microscopics per se, we will simply restrict ourselves to understanding the transport the fact that there are transport coefficients, and this is its value for this particular material or this particular gas. We will take that to be a given and go forward from there. So these are the three things. These are the three major things to keep in mind. The other thing is, okay, so the natural question that comes to mind is we've been talking about the distinction between microscopics and macroscopics, but what's the boundary line? Yeah. So turns out the boundary line is a little fuzzy. The boundary is it's just that in order to operate in the continuum limit, we need, again I emphasize roughly speaking, the number of particles in some macroscopic volume to be much larger than 1. Notice the two vague adjectives in this sentence, in some macroscopic volume. Yeah. So what do you mean by some macroscopic volume? Say this room that I'm standing in, the size of this room is say about 10 feet or maybe a little more. So a representative macroscopic volume would be say 1 cubic foot. Okay. Certainly not 1 cubic centimeter, right? Maybe 2 cubic foot, 2 cubic feet or 5 cubic feet, but certainly not 1 cubic centimeter or 1 cubic inch. Yeah. So this is what I mean by saying some macroscopic volume, some reasonably large volume. Exactly how large it is depends upon the situation. In astrophysics, of course, 1 cubic foot doesn't make much sense. You would have to be talking about say of the order of a parsec or so. It all depends upon the situation at hand, exactly what you call a macroscopic length scale or a macroscopic volume. Yeah. So you are justified in using the continuum limit if the number of particles in some representative macroscopic volume is much greater than 1. So here is the other fuzzy thing in this definition. What exactly do you mean by much greater than? Yeah, are you talking about 10? Are you talking about 100? Are you talking about 1,000,000? Turns out again the answer is a little fuzzy. Ideally, you would like to have as many particles as possible in a macroscopic volume, so that when you are reasonably far enough from it, you're not able to discern the dynamics of each particle per se, but you're able to discern the dynamics of the collective ensemble. Yeah, you're able to say, for instance, if I make a statement saying the number density of particles or the number density of molecules in the room is so much, well, you're mentioning the word density, which means that implicit in this statement is the fact that there are many molecules. Yeah, only then the concept of density makes sense. Exactly how many? Are there more than 10 molecules, in which case do there have to be more than 1,000,000 molecules? Well, that in fact depends, and again in astrophysics, astrophysicists like to slide on thin ice, and there are situations where the number density is very small. Outer space, contrary to what's commonly stated, is not vacuum. It's there is matter out there. It's just that the matter is extremely tenuous, extremely thin, and yet one resorts to continuum description of the matter. And so many times the continuum limit becomes a little questionable in astrophysical applications. Be that as it may, we'll come to it when we deal with it, but in everyday situations such as the flow of air or something like this, the continuum description is very much valid in the following sense: the number of particles in some representative macroscopic volume is typically much larger than 1, because of which it's meaningful to talk in terms of to invoke macroscopic properties such as number density, pressure, and so on and so forth to characterize a continuum. So to expand on that just a little bit, here is an example of bulk properties from the microscopic kinetics. Yeah. So here's one example. Consider a gas whose molecules are in thermodynamic equilibrium, in that you can ascribe a definite temperature to it. The molecules have been bouncing around each other for a long time and have established an equilibrium amongst each other. And a consequence of this is that the molecules have a very definite distribution, F. By distribution I mean, say, the Maxwell-Boltzmann distribution. So on the x-axis, say you might have speeds. On the y-axis you might have the probability of finding particles in a certain speed range. Yeah. So I'm sure you've come across this, and so that would be the distribution would be characterized by this distribution function f, and for a Maxwell-Boltzmann distribution this is just an exponential as you know. Now, what is an example of a bulk property that is derived from this distribution? Say the total number of molecules in a box. Yeah, the molecules are characterized by a Maxwell-Boltzmann distribution, and you integrate this distribution over all space d cube x and all velocities. Yeah, so you integrate the distribution function over all space and all velocities, and the normalization works out to be the total number. Okay, so this is the first most basic kind of illustration of how you derive bulk properties such as the total number from kinetics. So as I was saying, the total number is given by this integral where you're integrating over all space as well as all velocities. Yeah, so d cubed x as well as d cubed v. Yeah. What if I was not interested in the total number per se, but I was only interested in the number density, say the number per centimeter cubed. Yeah. So if I wanted that, then I would say I would simply write n is equal to integral of f d cubed v. This is supposed to be a 3. Let me write this again. N is equal to integral of f d cubed v, and this would be this would give me the number per centimeter cubed. Okay, that's because I'm not integrating over d cubed x. If I integrate over d cubed x, then the per centimeter cube goes away and I get just total number here, which is a dimensionless quantity. So here is an example, as I said, of a macroscopic quantity such as the number, or for that matter the number density, derived from a microscopic quantity, not quite microscopic, I would call it a mesoscopic quantity, which is the distribution function f. Yeah, here is an example of what I was just saying. The number density n in per centimeter cubed would be just this quantity f integrated over d cubed v. If you are interested, say, in the average velocity, yeah, so what you do is you just stick the velocity in here, and you integrate over the distribution function. So the basic normalization of the distribution function is given by f d cube x d cube v, which gives you the number. And if you wanted to find out an average velocity, if there is any, for instance, is there an average velocity to the air in this room? In other words, is there a breeze flowing through it or not? Yeah, so there may or may not be an average velocity. If there is, you could find that out by doing this to the distribution function. The point I'm trying to make here is this is how you derive a macroscopic quantity like the velocity from a microscopic quantity, which is the distribution function. This is the basic point I'm trying to make. Yeah, and now, so the average velocity is one thing, but something that you might be a little more familiar with would be, for instance, the kinetic energy, the average kinetic energy, average of half mv squared. Well, what do? Instead of velocity here, instead of v here, you just stick half mv squared into the same integral, into this very same integral. Look, this and this are the same, the integrand are the same, except you have stuck a half mv squared here. Yeah, so you perform this integral. I mean, I've just shown one single integration. It's really a 6-dimensional integral, 3 dimensions for space and 3 dimensions for velocity. Yeah, so you perform this integration and you get the average of the quantity half mv squared. And we know that for a thermal distribution, in other words, a distribution that's characterized by a Maxwell-Boltzmann distribution f, we know that this half mv squared, this is equal to 3/2 kT. So here's an example of how you derive the temperature of a gas, T, from the microscopic distribution function. Yeah, you see you're going from the microscopic distribution to the temperature. Yeah, so the microscopics concern themselves with kinetics. things like collision and so on and so forth. But if you wanted to get a macroscopic quantity like the temperature, which will be used in our study of fluids, in the study of the continuum, this is how you do it. Yeah. So this is an example of how you get a bulk property such as the temperature from the microscopics. And you know the pressure is simply equal to N K T. Many people like to say KB. Sorry. P equals N K Boltzmann T. So the KB is simply the Boltzmann constant. So the pressure is, so this is a macroscopic quantity and this is a macroscopic quantity, and the product of them with the Boltzmann constant, of course, gives you the pressure. So you see, the pressure of a gas, which is essentially represents a statistical average of the force per unit area due to molecules striking the walls of a container, it's just thus it's really a macroscopic concept, and that can be derived from and so it's related to these two macroscopic quantities, density and temperature, and it can it can be linked to the microscopics in this way. The density is related to the microscopic like this. Yeah, the distribution function is a microscopic quantity, and you integrate that to get the density, and the temperature is linked to the microscopics in this manner. Yeah, we just did that. This is how the temperature is linked to the distribution function here. So here we have about how many examples? About 3 examples of how you squeeze out macroscopic quantities such as pressure, number density, temperature, and things like this from the microscopic quantities which are from microscopics of the gas, which are characterized by the distribution function, right? So having done that, so the whole point of this slide was how you derive, was to justify our description of fluids as a sub branch of continuum mechanics, as opposed to the mechanics of discrete point bodies, right? And so that was that. The other basic question you might have in your mind is, we keep talking about this thing called fluids, and you might know that fluids comprise, I mean, when we normally say fluids, it includes both liquids as well as gases. There are differences, but nonetheless they're both considered fluids. On the other hand, in everyday life we come across solids, a piece of rock or so what really is the distinction? Yeah. The distinction is kind of subjective, but one central difference between solids and fluids is that fluids are characterized mainly by the response to what are called shear forces. Okay, what one means by shear is a force that is not normal to a surface. Say you have a surface like so, and you're pressing against it. There's a normal force, whereas a shear force is something that's trying to deform the surface like so. Okay, a shear force is something that can be tangential to the surface, either in this way or in this way. Okay, so consider for instance, this kind of a situation where you have an element of fluid like so, and you're trying to deform it with a shear force like this. Notice the force is not normal. It's not normal like this. It's not like so. It's shearing like so. Yeah. So you're trying to distort this element so that the square, which is ABCD, you're trying to make it a parallelogram ABC dash D dash. Yeah, that's what you're trying to do. In this case, this is a solid element and this is a fluid element. As such, this diagram does not tell you that much. But the main thing to focus is that here, fluids cannot resist shear. When you apply a shear force like so, a fluid element flows. The top surface here, it simply keeps the top surface simply keeps sliding over the bottom surface. Okay. When you apply a shear force to an element of fluid, it flows. Whereas you apply a shear force to an element of a solid like here, it tends to snap back to its original position. Okay? This is what elasticity is all about. You try to deform and it snaps back. Whereas fluids, on the other hand, the fundamental difference between a fluid and a solid in some sense is its ability to withstand shear. Okay, you apply a shear force being any force that's not normal to the surface, any force that's parallel to the surface, either this way or that way, or a combination of these. Yeah. So here you see, here's an example of a force that's parallel to the surface, and so you're applying this kind of a shear force. A solid tends to withstand shear, it tends to snap back, whereas a fluid cannot do that. The surface simply slides continuously over the bottom surface and the fluid flows. Okay? So of course there are so this is what I mean by saying solids can be elastic. Whereas a fluid deforms or flows continuously in response to an arbitrarily small shear. The shear can be arbitrarily small, and yet the fluid will start flowing. Yeah. There are complications. There are materials which display characteristics of both viscosity as well as elasticity. Viscosity refers to fluids. Elasticity refers to solids. In some sense they are the same, but for instance, nanoparticles of water. You think of water as a fluid, right? Turns out that when you confine water to about a nanometer scale droplet, it starts behaving like a solid. Very, very strange, but true. Yeah, we will not be going to these complications. We will restrict ourselves to what are called Newtonian fluids, for which this is not true. Okay, we don't bother about complications like viscoelasticity. The main point of this slide is that the boundary line between solids and fluids is its capacity to withstand the fact that fluids cannot resist shear in response to even an arbitrarily small amount of shear. It flows. So this is the main thing. And how exactly do fluids respond to shear? Well, here you go. So consider what this is these arrows here. These represents vectors that show the magnitude of x directed velocity as a function of y here. So this is y and this is x. Okay, so the velocity is only in the x direction. So what's written as uy here is essentially the x component. U is the x component of velocity, and that's the only component of velocity there is. So what this is saying, what this diagram is saying here is that the x component of velocity varies with y. So this, for instance, could be representative of a fluid like, say, honey. Consider honey in a box, yeah, and you apply a shear force, you apply a force to the top layer of honey. You can imagine that the top layer will flow smoothly, the top layer here will flow smoothly, whereas that's not true of the next bottom layer here. That will not flow with the same velocity as the top layer. The velocity of the next bottom layer is slightly smaller, and the velocity of the layer below that is even smaller, so on and so forth, until the time you come to the very bottom of the vessel where the velocity might well be almost zero. Yeah, so it's almost as if these different layers are connected by little rubber bands like this. Okay, so when you're trying to slide the top layer over this, there are these imaginary rubber bands which are trying to prevent the sliding. Okay, and this is what viscosity is all about. In other words, if there is a velocity gradient, if there is a ux as a function of y, yeah, you see the ux is large here, not so large here, even smaller here, so on and so forth. If there's a gradient in ux as a function of y, viscosity tends to reduce that velocity gradient. Yeah, so this solid line, this would have been the original profile, and that tends towards this dotted line here. And so this is what viscosity is all about. Viscosity is that phenomenon which tends to reduce the velocity gradient. Okay, and this is something that's peculiar to fluids. We will come to a more formal definition of viscosity in due course, but for the time being, since we talked about the distinction between solids and fluids, and we sort of hinted at the fact that fluids are characterized by viscosity, whereas solids are characterized by elasticity. Without going into definitions of elasticity, since we're mostly concerned with fluids, I thought I would sort of give you a general idea, broad definition of what viscosity is all about, and this is it. Viscosity is that property of a fluid which makes it resist shear. Although it does flow, okay, a fluid cannot resist viscosity. A fluid cannot resist shear, and how much it flows depends upon the viscosity inherent in the fluids. And you can think of viscosity as that property which makes little rubber bands connect different layers of the fluid. Yeah? And these rubber bands are preventing the top layer from sliding arbitrarily over the bottom layer. The stronger this rubber band is, the more the viscosity, which is why, say, you think of honey as a more viscous fluid than water. By the time you reach the bottom layer here, the velocity would be almost zero. Yeah? So the gradient is very large, whereas that's not so with in case of what we normally think of as a less viscous fluid, which would be water, right? So the next concept I would like to talk about is something called stress. The kind of stress that we're most familiar with is just pressure. Yeah, and that would be what's called a normal stress. And so a normal stress would be basically a normal force, dFn dA, where Fn is a normal force. Normal meaning here you have a surface and you have a force like this which is normal to the surface. Yeah, so this is the scalar pressure that we're familiar with, but this need not be the only kind of and this is one kind of stress. You can also, you guessed it by the amount of emphasis I was placing on the word shear in the previous slides. We will be concerned not only with normal stresses but also with shear stresses. Yeah. So the kind of stress that arises from shear forces. So suppose you have an area element like so, like this. Yeah, and you have a shear, a force that's not necessarily always normal. This would be the normal force, but you can also have a tangential force, a force that's tangential to the surface, and this would be what's called a shear force. The tangential force can be like so, or also into the plane of the screen. So either way, it's parallel to the surface, and you can always define this quantity dFs dA in analogy with this quantity dFn dA, right? So the only difference being, we call this a shear stress, we call this a normal stress, simply because this arises from shear forces and that arises from normal forces. So as such, there is no big distinction between these two kinds of, it's just that we are a little more familiar with normal stresses than we are with shear stresses, simply because we are more familiar with the concept of pressure. Turns out that a normal pressure is not all there is. There are also these shear components, and these two kinds of stress can be combined into one unified kind of description. So what's it got to do with viscosity? Well, for a wide class of fluids called Newtonian fluids, which is the only kind of fluid that we will be concerned with in this course, the shear stress, the quantity tau s here, which we defined here, which is essentially the ratio of dFs to dA, where dA is the differential surface area, is proportional. Is observed to be linearly proportional to the velocity gradient. So the velocity gradient we encountered here, you see, there's a gradient of the y of the x component of the velocity as a function of y, right? So that's what this is. This is the du dy. This is the du dy that we encountered. Turns out that the shear stress is linearly proportional, and the proportionality constant is this mu. Yeah. And this mu is called the coefficient of dynamic viscosity. Okay, so you can see how intimately connected the concept of viscosity is with the concept of stresses. Yeah, and the stresses need not only be normal. Consider an imaginary cube like this. So the normal stresses on this cube. Let's see. Yeah, so this is phase 1, this is phase 2, this is phase 3, and so on and so forth. The normal stresses would be what are called the normal stress on phase 3 is the one which is pointing that way. The normal stress on phase 2 is the one which is pointing this way, and I call this tau 3, just a notation. Yeah, and I call this tau 2. What these subscripts mean are the stress on phase 3, yeah, which is arising out of a force that's also directed along the direction 3. Here the 2 means the stress on phase 2 which arises out of a force that's also in the direction of the outward normal characterizing phase 2. Okay, but as you can see, tau 3 is not the only kind of stress there can be. There can also be a tau 3 there can also be a tau 3 there can be a tau 3 and there can be a tau 3 yeah. So and the tau 3 it would be this, and the tau 3 would be this, and these two are what are called shear stresses, because these stresses arise from forces that are tangential to the surface, whereas tau 3 is a normal stress. And there's no real need to strongly differentiate between these three kinds of stresses. It's just that one is normal, the other two are tangential. You can consider them in one unified kind of description, and we will see why the concept of shear stress, the concept of shear stress is central to viscosity because of this. Yeah, it's experimentally observed that the shear stress is linearly proportional to the velocity gradient, and the constant of proportionality is this coefficient of dynamic viscosity. And the components of these of the stresses form what are called a tensor. The tensor is simply a matrix. The tau, the elements of which are tau 3, tau 3, tau 3, so on and so forth. Okay, some of them are shear stresses, some of them are normal stresses. The normal stresses are the ones in which these two indices are the same. For instance, tau 1 or tau 2 or tau 3. All the other off diagonal elements are called shear stresses, right? So from now on we will start talking about having talked a little bit about how fluids are characterized, how they are different from solids, and what's the main dividing line between solids and fluids. We will start talking about the study of fluid kinematics, which is essentially a study of the appearance of motion. Okay, for instance, displacement, velocity, acceleration, rotation, and so on and so forth of fluid elements without explicitly considering the forces that are acting on them.